Hello, everyone, and welcome to Lecture 14 of Computer Architecture. Today, we're going to talk about floating point arithmetic. So last time we started talking about how to represent floating point numbers. Today, we're going to talk about how to do arithmetic on these numbers on paper and in hardware. So first, a review of last time. We saw how we can support real numbers in decimal by having a point and some digits to the right of the point. And what this means when we have digits to the right of the point is that each digit is going to be multiplied by the 10 to the power of negative the position with respect to the point and added to the total. And same thing with binary. If we want to support real numbers in binary, what we can do is we can have a point and then bits to the right of the point. And what this means is that these bits are going to be multiplied by 2 to the power of negative the position with respect to the point. And this we can support real numbers in binary. We saw how we can convert a fraction or a real number in decimal to a number in binary. For the part to the left of the decimal, it's the same. You divide by 2 and take the remainder. For the part to the right of the decimal, the way that you do it is you multiply by 2, and then you take the 1 or 0, whatever digit was to the left of the decimal after you multiply by 2, and then these digits are going to be your final answer in binary for the value of this number in decimal. We then looked at how we can represent real numbers in hardware, given that we have a limited number of bits. Usually, if you want to store these real numbers, maybe we have a 32-bit register that we would like to store this number in. So the question was, how can I represent real numbers using just 32 bits? One possibility was fixed point, and we saw how with fixed point, we simply said, okay, if I have 32 bits, I'll consider that some of these bits are going to be the bits to the left, and some of these bits are going to be the bits to the right. So maybe 16 bits are the bits to the left, and 16 bits are the bits to the right. And we have this imaginary point in between these 16 and 16 bits. And we call this fixed point because the decimal point was in a fixed position with respect to the bits in the 32-bit word. But we saw that the limitation of fixed point is that we have very limited range. So for example, we saw how the smallest number that we can represent if we use this fixed point representation of 16 bits to the left, 16 bits to the right, the smallest number we could represent is 2 to the negative 16, which is something times 10 to the minus 5. And the largest number we could represent was 2 to the power 16 minus 2 to the power negative 16, which is something times 10 to the power of 4. So it's in the order of the 10,000s. And we saw how this range is very limited. For example, we cannot represent very small numbers like the gravitational constant. We cannot represent very large numbers like Avogadro's number. So what we did is we wanted to find an alternative representation that gave us better range. And for this reason, we looked at floating point. So to motivate floating point, I first introduced scientific notation, where a number can be represented using just a significand and an exponent. And so rather than writing all of these zeros for 920 million, we can simply write 9.2 times 10 to the 8. So rather than needing 9 digits to represent this number, we just need 3 digits. 2 digits for the significand in this case, and 1 digit for the exponent. And when we normalize a value in scientific notation, we make sure that there's only 1 digit to the left of the decimal point. And leveraging this notion of normalized scientific notation, we did the same thing for binary numbers. So rather than writing this binary number over here, we represented it as 1 point something times 2 to the power of something, where this something this something obviously we represented in binary. And now that we've done this, what we can do to store this number is simply store the significand and the exponent. And we even said that this number, this 1 here to the left, is always there, so it's redundant to store it. So really, we only need to store the numbers to the right of the significand and the value of the exponent. And this is exactly what we did in floating point numbers. So we said that there's a standard for storing floating point numbers defined by IEEE. This came because historically there was a lot of different people who were representing real numbers in different ways, and that made their codes unable to operate together. So IEEE standardized standard that is now universally adopted, and there's two representations, one for single precision, which uses 32 bits, and one for double precision, which uses 64 bits. And the format is as follows. We have 1 bit for the sign, and then we have an exponent and a fraction. The exponent is 8 bits in single precision, 11 bits for double precision. And the fraction is 23 bits for single precision and 52 bits for double precision. But this followed this idea of storing the exponent and storing the fraction and using them to reconstruct the entire real number when we need it. We saw how we looked at precision and range for these different representations, and we saw how precision, which is the number of digits that we can represent, is impacted by the size of the fraction, and the range, which is how large and how small the numbers we can represent are impacted by the size of the exponent. And that's where we left off. We did some exercises to show what is the precision of single precision and double precision, what is the range of the single precision and double precision bits. And we left off there. We still had the topic of how to represent 0 and what to do in case we have irregular events. And I will continue talking about those today. But before I jump into that, any questions about last time's material? Okay, so if there are no questions, I'm going to continue talking about what we were not able to cover last time, which was representing 0 and also representing irregular events, and then we will later then start talking about how do you do arithmetic using floating point numbers. So let's talk about 0. So if you remember, when we were looking at the largest and the smallest possible numbers that we can represent, I told you that there are two exponent values that are reserved. One of them was the all zeros exponent value, and the other one was the all ones exponent value. So to represent 0, first of all, we observed that the format we had cannot represent 0, and the reason is that we always assumed there was this imaginary or this hidden 1 to the left of the decimal point, and we were only storing the digits to the right of the decimal point. Well, if you look closely, we can't represent 0 this way because we always have a 1 here. So 1 times 2 to the power of anything, it cannot be made to be equal to 0. So to represent 0, what we're going to do is we're going to reserve the exponent that is all zeros, okay? And when the exponent is all zeros, we're going to refer to these numbers as denormalized numbers. So remember, a normalized number was a number where we always had one non-zero digit to the left of the decimal point. In the case of binary, there's only one non-zero digit, which is 1. And for denormalized numbers, we don't need to have we don't need to have a 1 to the left of the decimal point. And in fact, what we're going to do is we're going to reserve the exponent that is all zeros, and we're going to say that, okay, when this exponent is all zeros, then our number is not going to be 1 point something times 2 to the power of something. Our number is going to be 0 point something times 2 to the power of something. Okay, so when the exponent is 0, our number is going to be interpreted as a denormalized number, not as a normalized number. Now, how does this solve our problem? Well, it solves our problem because now if I want to represent 0, then all I have to do is set the exponent to 0. When I set the exponent to 0, it means that my number is of the form 0 point something times 2 to the power something, and I'll talk about what that something is later. But then what we can do is now we can set the exponent to 0. We can set the fraction bits to 0, and now we're going to have 0.00000 times 2 to the power something, which will be 0. Okay, so this reserved exponent that's all zeros, this is going to be used to represent 0, but it's also going to be used to represent denormalized numbers in general that are of the form of 0 point something times 2 to the power something. Okay, so let's look at this a little bit more formally. So if the exponent is 0, we're going to consider the hidden bit to be 0. And in this case, we're going to interpret the numbers as still the sign bit's going to be the same, -1 times -1 to the power of the sign bit. But now we have something changed. Rather than having 1 plus fraction, we're going to have 0 plus fraction. okay? And then times 2 to the power, rather than having exponent minus bias, we're going to have negative bias plus 1, or 1 minus bias if you want. Okay, so this is how we're going to interpret the value when the exponent is 0. Okay, and the way we were going to represent 0 here is we can simply set the fraction bit to 0. So if we set the fraction bit to 0, then we have negative 1 to the power of sign bit times 0.00000 times 2 to the power of negative bias plus 1. So if you kind of do it out, this comes out to become 0.0. Now, one caution here, here now we have two representations of 0. We have positive 0 and negative 0 because we're using a sign bit. But that's okay. It's kind of a quirk that we live with, and it's okay. But another benefit of denormalized numbers is not just that we can represent 0, but it turns out that we can also represent smaller numbers than we can represent with normalized numbers. So let's take a look at that. So what I can do is, so denormalized numbers can also be used to represent numbers that are smaller than the smallest normalized number. So for example, if I'm using single precision, if I set my exponent to be all zeros, and then I set my fraction to be something like this, 0, 0, 1, 0, 0, 0, 0. Okay, so what happens here? Well, here my number is going to look like this. It's going to be negative 1 times to the power of s. So here s will be 0 or 1. The fraction is 0, 0, 1, 0, 0. Since this is a denormalized number, I'm going to interpret it as 0 point the fraction. So it's going to be 0.001 and then a bunch of zeros times 2 to the power of negative bias plus 1. So in this case, it's going to be 0.001 times 2 to the power of negative 126. And if I normalize that, it becomes 1.0 times 2 to the power negative 19. Sorry, negative 129. Now, if you remember, the smallest normalized number that we were able to represent in single precision was 2 to the power negative 126. Okay? But now with denormalized numbers, what we can do is we can actually represent numbers that are even smaller. Okay? We can represent numbers that are even smaller. And the reason we can do that is because now this bit to the left here is 0, not 1. So by simply having smaller and smaller fractions, we can have smaller and smaller denormalized numbers. Okay? But there is a trade-off here. And the trade-off is that this 1.0 times 2 to the power of negative 129, over here the numbers the number here is actually has diminishing precision, right? Because now I have, for example, in single precision I have 23 fraction bits, but I've actually when I look at this number over here, I've wasted 2 of these fraction bits. So these 2 fraction bits are not going to be used. So instead we're going to have only these bits to the right that we can use to represent something meaningful. So the nice thing about denormalized number is that we can have smaller and smaller numbers compared to normalized numbers, but the trade-off is that we get diminishing precision. Okay, so to summarize, if we set the exponent to be all zeros, then we're going to interpret our number as our significand as being 0 point the fraction bits as opposed to 1 point the fraction bits. And the benefit of that is that we can represent 0 and we can represent even smaller numbers, but with diminishing precision. Okay, any questions about denormalized numbers? So someone's asking, can I repeat why we get diminishing precision? Yes. So here, when I have a normalized number, it's going to be 1 point something, okay? And that 1 point something is going to be 23 bits to the right of the point, okay? So I have 23 bits of precision, not including the one to the left of the decimal point, okay? But with denormalized number, now I have 0 point something, okay? So now I have, when I have 0 point something, well, this digit over here is not significant, and these 2 zeros to the right of the point is not significant. So if this was single precision, then the only significant digits I have here is the 21 remaining bits, okay? So now I have, so here, my 2 to the power negative 129, this could be 1, but here I could have a whole bunch of other things, right? So it doesn't need to be 1.0 times 2 to the power negative 29. It could be anything times 2 to the power negative 129. But this anything over here is only going to have 21 bits of precision, not 23 bits of precision, okay? And again, the 23 does not include the bit to the right, so it's actually 24 bits. So now I have 21 bits of precision instead of 24 bits of precision, and this is why we have diminishing precision. And the smaller the number with the denormalized numbers, the less the precision. So for example, we can have 0.000000 and then just a 1 here at the end. Okay, this is going to be a very small number, right? Because we're going to have, this is going to be 2 to the power negative 123 times 2 to the power negative 126. Okay, so if you add 123, if you add 23 and 126, you're going to get, a very small number. So you're going to get a 2 to the power of negative 126 plus 23, 149. Okay, so 2 to the power of negative 149, that's a much smaller number, but we're only going to have 1 bit of precision, right? Because it's going to be a whole bunch of zeros and then a 1 at the end. So we lose precision, but we get smaller and smaller numbers. And that's what I mean by diminishing precision. Any other questions? Okay, well, now let's look at what we do with the other reserved exponent. So what we would like is we would like a way to represent unusual events. And what do I mean by unusual events? Well, let's take a look at certain things that could happen when we're operating on floating point numbers. So we need a way to represent special values that arise from unusual events. These could be things like overflow. So if I add two numbers and I get overflow, I get a number that is much larger than any number that I can represent in my range. Okay, I get a very large number, or maybe if I divide by 0 or something. So here I want to be able to represent positive and negative infinity. So if I have overflow, I want to be able to say that, okay, this number is positive infinity or negative infinity. Okay, that way, if I don't have to check for overflow every time. I simply store the number as positive infinity, negative infinity. If I multiply it later on by something else, the final result stays positive infinity or negative infinity. We also want to be able to represent undefined results. So maybe I divide 0 by 0, or maybe I subtract infinity from infinity. Okay, so if I subtract infinity from infinity, so where did this infinity come from? Well, it came from overflow. So if I have a number that overflows and another number that overflows, and I subtract a number that overflows from another number that overflowed, the value is valid theoretically, but because of my hardware limitations and the size of the numbers I can store, when I subtract infinity from infinity, the result's not going to be infinity, but it's going to be undefined. Okay, so we need a way to represent undefined results. And usually we represent this using this value nan, which stands for not a number. Okay, so I want to be able to represent positive and negative infinity, and I want to be able to represent undefined numbers, so not a numbers. And what we're going to do is we're going to use the reserved exponent that is all ones for this purpose. Okay, we're going to use the reserved exponent that's all ones for this purpose. How are we going to use it? Well, simply what we're going to say is, if the exponent is all ones and the fraction is all zeros, then the value will be interpreted as positive or negative infinity depending on the sign bit. Okay, the nice thing about this is that if a value overflows, we store positive and negative infinity, and we don't have to check for overflow every time. We simply use it later on in other calculations, and my final result will stay in positive or negative infinity, and I can just check my final result. I don't have to check all the intermediate results. And then in the other case, if my exponent is all ones and my fraction is not all zeros, then this will be interpreted as not a number. This happens when we have something that is illegal take place. And again, we can, rather than checking for nans every time, usually we simply kind of continue using our calculations. But then a nan with added or multiplied with anything else is going to continue to be a nan. Okay. So this is what we use the reserved exponent that is all ones for. We use it to represent positive and negative infinity in the case of overflow, and we use it to represent nans in the case something illegal was done. Okay. Any questions about infinities and nans?
Professor, can you give us an example about how we might get infinity or NAND?
Yes, so the way we get infinity is if we add two very large numbers such that their sum cannot be represented within the range of the range that we allow, right? So we said that there's a limited range that we can get using with floating point numbers. So if we add or multiply two numbers that are very large and their result is outside of this range or greater than this range, that is where we will simply set our result to positive infinity or negative infinity. Okay, so that's the case for positive and negative infinity. For NaN, this has to do with a whole bunch of illegal things that we might do. And two examples I gave here is dividing 0 by 0 or subtracting infinity from infinity. Okay, so in this case, both of these have undefined results. And if you try to do something like this, the result will be a NaN. Okay. Other questions? Okay, well, if there are no more questions, then that's all I have to say about representing floating point numbers. So today what we're going to do is we're going to talk about floating point arithmetic. So how to do arithmetic with floating point numbers. So someone's asking, what if we have infinity with a fraction part? So you can't have that. So let me go back. Okay, so here, if the exponent is all ones, the fraction has to be all zeros for this to be interpreted as infinity. Okay, if the fraction is not all zeros, then this will be a NaN. Okay, so you can't have infinity with a non-zero fraction. Okay. Okay, so today we're going to look at floating point arithmetic. How can we do arithmetic with floating point numbers? All right. Let's first start by talking about floating point addition. And before I do that, I'm going to look at how we add the numbers in decimals. So let's say I have this 4-digit decimal example. I have 9.999 times 10 to the power 1 plus 1.61 times 10 to the power minus 1. So let's say I want to add these two numbers, okay? So can I simply add them like this? Can I add 9.999 to 1.61 over here? So I add 9 plus 0, 9 plus 1, 9 plus 6. Can I do this? Right, I can't do it. Why can't I do it? Right, exactly. They need to have the same exponent. They need to have the same exponent. So I can't simply add these two significands over here because they don't have the same exponent. What I need to do is I need to first align them so that they have the same exponent. Okay, and what that means is I'm going to take one number and shift it so that it has the same exponent. And usually what we do is we will shift the smaller number and align it to the larger number. So here, if I'm adding these two numbers, I will shift the smaller number, which is 1.61 times 10 to the power minus 1. I want both of these to be 10 to the power 1. Okay, so what I'm going to do is I'm going to shift this decimal point twice to the left so that this 10 to the minus 1 becomes 10 to the power 1. Okay, so the first step is going to be to align my decimal points by shifting the number with a smaller exponent. And how much do I shift it? I'm going to shift it twice. Where do I get twice from? Well, 1 minus negative 1 is 2. And that's why I'm going to shift it twice, because I want to add 2 to this number over here. And then to do that, I'm going to shift left twice over here. So after I align the decimal points, I get this. I get 9.999 times 10 to the power 1 plus 0.016 times 10 to the power 1. Okay, can I add now? So now I can add because they have the same exponent. So what I'm going to do is I'm going to add these two numbers just like I would add an integer. Okay, and the sum is going to have the same exponent. Okay, so 9 plus 6 is 15, so I'm going to put a 5 down here and a 1 up here. 9 plus 1 plus 1 is 1, so I'm going to have a 1 down here and a 1 up here. 9 plus 1 is 1, so I have 0 and 1. Then 9 plus 1 is, sorry, 9 plus 1 is 10, so I'm going to have a 10 over here, and I will carry down this exponent over here. Okay, so the first step is to align my two numbers by shifting the number with a smaller exponent, and the second step is to add the two significants. Okay, and we get this result, and the exponent remains the same. Okay, now that I've added the two numbers, well, now my sum is no longer normalized. So I have a sum, but the sum is no longer normalized. So what do I want to do? The next step I would like to do is I would like to normalize this number. Okay, how do I normalize it? What am I going to do? Well, to normalize it means that I only want to have one value to the left of the decimal point. So what I'm going to do is I'm going to take this decimal, shift it one to the left, and then I'm also going to increment my value over here. Okay, I'm going to increment my exponent to become 2. Okay, so this is how I normalize. I'm going to normalize the result. So I'm going to get this value over here, 1.0015 times 10 to the power 2. Okay, that's how I normalize. By the way, if I was doing subtraction, I could have gotten here. Here it happened. I was doing addition, and it happened that I got overflow, and I need to normalize. If I was doing subtraction, I could have gotten 0 point something. So I could have gotten 0.43 something, right? And then I would have to normalize in the opposite direction. So in this case, I would move the decimal point to the right, and I would decrement the exponent. Okay, but in this case, we're adding, so we got overflow, so we're going to normalize by moving the decimal point to the left. Okay, so here, after we normalize, now we have a problem. Like I mentioned at the beginning, we're looking at 4-digit decimal values. Okay, so we assume we have a fixed number of digits that we are going to represent. So now that I normalized, now I have more digits of precision that I want. I have 1, 2, 3, 4, 5 digits, but I only want to represent 4 digits. So what do we do in this case so that we can reduce the significant to just use 4 digits? Right, exactly. We're going to round it. So what we do is we can round. So we're going to take this 1.0015 and we're going to round that to 1.002 times 10 to the power 2. And this is our final result. Now, one thing to be aware of here is I might round, and the rounding may result in may cause my value to no longer be normalized. So, for example, if this value before rounding was something like maybe it was 1.9998. Okay, when I normalize, or sorry, maybe it was 9.9998. Okay, so if I normalize, if I round, what's going to happen is that the rounding is going to result in overflow again, and I'm going to have to normalize and round again. So it doesn't happen too often, but it's possible that after I round, my value becomes not normalized anymore, and I'm going to have to renormalize and round again if necessary. Okay. So this is how we do how we add decimal values, decimal real numbers. Let's take a look at how we can do the same thing with floating point numbers. Sorry, with binary real numbers represented in floating point. So let's say I had this example over here. I have 1.111 times 2 to the power negative 3 plus 1.100 times 2 to the power negative 5. Okay, and you can think a lot on your own about how you represent these as floating point numbers. So now can I add these two numbers? I can't add them because they don't have the same exponents. So what do I need to do? It's the same procedure that we did with decimal, right? It's the same procedure that we did with decimal. What do we do first so that we can add them? We need to align the decimal point. Exactly. We need to align the two numbers. How do we align the numbers? Well, we're going to look for the smaller number. Okay, so we're going to align the binary point by shifting the number with the smaller exponent. So the number of the smaller exponent is 2 to the negative 5. So what we're going to do is we're going to take this decimal point and we're going to shift this point and we're going to shift it 2 to the left. Okay, why 2 to the left? Where did I get 2 from? Right, exactly. So a negative 3 minus negative 5 is 2. Okay, so the difference between I know how many positions I need to shift to the left or to the right, but in this case going to the left because we're always shifting the number of the smaller exponent. I know how many positions I need to shift by subtracting the exponents. Okay, so what we're going to do is we're going to shift this number, this point 2 to the left. So this is going to become 0.011 times 2 to the negative 3. Okay, so it'll become 0.011 times 2 to the negative 3. Now that I've aligned the two numbers, now what do I do? Now I can add them. Okay, so how do I add them? Well, the significants are just going to be added as if I was adding integers. I'm going to do 1 plus 1. That gives me 1 0. Then I have 1 plus 1 plus 1. That gives me 1 1. And 1 plus 1. That gives me 1 0. So I have 0 here, 1 here. 1 plus 1 plus 0. That gives me 1 0. Okay. So after I add, I'm going to get this significand over here, and the exponent is just going to be the same. Okay. The exponent is going to be the same. Okay, so step 1 is to align the smaller number to the larger one. Step 2 is to add. What is step 3? What do I do after I add? I normalize, exactly. So in this case, to normalize, I'm going to shift the point 1 to the left, and I'm going to decrement my exponent. Okay, so I'm going to normalize. I'm going to get 1.0010 times 2 to the power negative 2. Okay, and what's my next step now that I normalize? Now I have more than 4 bits, but I only want 4 bits. So what am I going to do? Right, I'm going to remove this 0 on the right. This 0 could have been a 1, right? This could be 1 or it can be 0. So in general, what do I do? I'm going to round, exactly. So the last step is to round. So I'm going to round in this case, and I'll get 1.001 times 2 to the negative 2. Okay, and with rounding, I could have had 1.1111 over here. Okay, in this case, if I rounded, I could have had overflow again, and I would need to renormalize. So here it's round and renormalize if necessary. Okay. So again, 4 steps. Please remember these. Maybe write them down so you don't forget them because we're going to refer to them later on. 4 steps: align, add, normalize, and round. Okay. Any questions about how we're doing floating point addition? Okay, if there are no questions, then next what we're going to talk about is how do we do this in hardware? Okay, how can we do floating point addition in hardware? Someone's asking how do we round in binary? There are different ways to do it actually, and I'll talk about that later. Okay, but for now, just assume that we have a way to round in binary. Okay, so how do we do this in hardware? So what we want to do is we want to build a hardware unit that does floating point addition for us. Let's see how to do that. So what we're going to do is we're going to start off with 2 numbers. Remember, we're using the IEEE standard format, so each number is going to have a sign, an exponent, and a fraction. Okay, so I have 2 numbers, each one has a sign, an exponent, and a fraction. They're stored in some register, and what I'd like to do is I'd like to build a hardware unit that adds these 2 numbers. Okay, so what was the first step? What was the first step in adding? Who remembers? Aligning, exactly. So the first step is to align the two numbers. Which number am I going to align? I want to align the smaller number to the larger number. So I want to identify which one of these numbers is smaller, and I want to shift it and increment its exponent. Okay, how do I find which number is smaller? Well, simply I'm going to compare the exponents, right? I'm going to find which exponent is smaller. So the first step is to pass the two exponents to a small ALU. The reason I call it a small ALU is because the exponent is only 8 bits, right? Remember, with the single precision, the exponent is 8 bits. With double precision, it's 11 bits. But 8 and 11, these are small values. So we're going to have a small ALU that's going to subtract the exponents and find the difference. Now, from the difference of the exponent, I'll be able to know which of these numbers is smaller. And once I know which number is smaller, what do? I want to take the smaller number and I want to shift it, right? I'm going to take the smaller number, I'm going to shift it. So how do I select the smaller number? What hardware unit do we use to select? A multiplexer, exactly. So what we're going to do is we're going to take the two fractions and we're going to pass those to a multiplexer. This multiplexer is going to select the smaller fraction, the fraction that corresponds to the smaller exponent, and it's going to shift it to the right. How do I know which one to select? It's the smaller one, so I'm going to look at the exponent difference exactly. How do I know by how many positions to shift? Again, from the exponent difference, okay? So what we're going to do is we're going to pass the exponent difference to a controller, and the controller is going to control the mux to select the fraction for the smaller exponent. And it's going to control the shift unit over here to shift by the appropriate number of bits, okay? So now what we have is we have the the fraction of the smaller exponent now shifted, okay? What about the fraction of the larger exponent? Do we do anything to that, or do we keep it the same, keep it as is? Yeah, we're going to keep it the way it is, exactly. So we're going to have another multiplexer, and this multiplexer this time is going to select the fraction of the value that has the larger exponent, and it's going to keep it as is. Okay, so now we have the number with the smaller exponent aligned or shifted, and the number with the larger exponent. Now what do we do with these two numbers? We're going to add them, exactly. So I'm going to take these two numbers and I'm going to pass it to an ALU. I call this a big ALU, and the reason is that the size of this ALU is going to be how many bits? The number of fraction bits. So for single precision, it's going to be a 23 bits. For double precision, it's going to be 52 bits. Okay, so this small ALU corresponds to the size of the exponent. This big ALU corresponds to the size of the fraction. So after I add the fraction, now I have the sum. What's the exponent going to be? Which exponent is going to be, all right, it's going to be the same as the number with the bigger exponent. So what I'm going to do to get the exponent for my sum, I'm going to take the two exponents, okay, and I'm also going to pass those to a multiplexer, and I'm going to select the exponent, right? I'm going to pass the two exponents to the multiplexer, and I'm going to select the exponent that corresponds to the larger number, and that's going to be the exponent of my sum. Okay, so now I have my sum, the sum of the significand, and the exponent of the sum. What's my next step after adding? So I do align, then I add, then what? Normalize, exactly. And then I'm going to normalize. So what do I do to normalize? What did I do when I normalized? I took the significand and I shifted it. And I took the exponent, so I shifted the significand. What did I do with the exponent? I increment or decrement, okay, depending on in which direction I'm not normalized anymore. Okay, so I'm going to take the significand and I'm going to shift it left or right, and I'm going to take the exponent and I'm going to increment it or decrement it, and by doing this I would have normalized. Okay, now how do I know if I need to normalize? How do I know if I need to normalize, and how do I know whether I should shift left or shift right, and how do I know whether I should increment or decrement? What do I look at? Right, if we have overflow in the addition, okay? So if we have overflow in the addition, or that means my number is too large, I need to normalize by shifting left. Or if my number is too small, so I have a whole bunch of zeros in the uppermost bits, then I need to normalize in the other direction, okay? So to know if I need to normalize or not, I'm going to take the result of the addition, I'm going to pass that to the controller to see if I have overflow, and then based on that, the controller is going to tell this increment decrement unit whether or not it should increment or decrement, and it's also going to tell the shift left or shift right unit whether to shift left or to shift right, or not to shift at all. Okay, so by doing this, now I can normalize. And then what's the final step? Now I have my normalized significand, my normalized exponent. What do I do then? Someone's asking, shouldn't we add the one from what's on the left of the exponent before we add? Yes, of course. So there's the implicit one. So someone commented that there was the implicit one. And of course, that implicit one is going to be coming in from here into the big ALU. Okay, of course. So the big ALU is not precisely 23 bits. It has an additional bit for that hidden one. Okay, so that's a good observation. Okay, so after we normalize, right, we're going to round. So we're going to take these values, then we're going to have some rounding hardware. Okay, I'm not going to go into the details of that. We're going to have a rounding hardware that takes these values and rounds. Okay, and after we round, we have our final result, our exponent, our fraction, and our sign. Okay, but there's one catch here. What did we say when we round? What could happen? Right, we may have overflow, so we may need to normalize again. Okay, so if we round, we may need to normalize again. So in this case, what we're going to do is we're going to take our values over here after rounding, and we're going to bring them all the way back and pass them through normalization to get normalized the second time. Okay, so what we're going to do is we're going to take these values over here, the exponent and the fraction, and we're going to bring them all the way back. Here, we're going to bring this value all the way back. Okay, and we're going to pass that on the second time to the shift unit, and we're going to take this exponent and we're going to bring it all the way back, and we're going to pass that in case we need to renormalize. Okay. Someone's asking, can we repeat how the controller knows if we need to decrement the exponent? Well, when do we decrement the exponent? We decrement the exponent if we are normalizing. And how do we know if we're normalizing? We know if we're normalizing if our value is too large or too small. Okay, so here we take the value from the result of the addition, we pass that to the controller. The controller checks if the value has overflow, it means we need to shift the decimal to the left. If the value has many zeros on the left, it means we need to shift the decimal to the right. And based on that, the controller tells these units whether to increment or decrement and whether to shift left or shift right. Okay, or maybe in most cases, we're probably not going to shift and we're probably not going to increment or decrement. Okay. Any questions? All right. Well, if there are no questions, then this is a floating point adder. This is how we add floating point numbers. Now let's look at, before that, just a few comments about the floating point adder. So you'll notice that our floating point adder is much more complex than our integer adder. Our integer adder was just an ALU. But our floating point adder, we have compare the exponents, we have multiplexers selecting, we have shifting, we have another ALU, we have rounding. So obviously all these operations take a long time. And because they take a long time, we usually don't do them in one cycle. Okay, floating point operations usually take multiple cycles. Now, what we could do is we could increase the duration of the cycle so that we can fit all these operations in one cycle. But the disadvantage of that is if we increase the duration of the cycle, it's going to increase the cycle for all the other instructions. Okay, so if all the other instructions need much less time, increase the duration of the cycle will make all those other instructions take more time unnecessarily, and that's why we usually just we don't want to slow down the clock because we don't want to penalize other instructions. We're simply going to let the floating point operations to take multiple cycles. Okay. So the floating point adder can usually take several cycles, and it can be pipelined, which kind of it reduces the impact of that. And we'll talk about pipelining later, so don't worry about pipelining for now. We will talk about pipelining later. Okay, let's quickly talk about floating point multiplication. I'm not going to cover hardware, but I'm just going to kind of walk you through the steps of floating point multiplication. In decimal, if we want to multiply two numbers, what do we do? If I'm multiplying two numbers, what do I do in decimal? Do I need to align if I'm multiplying? No, we don't align. What do we do? Right, exactly. We just add the exponents and we multiply the significance. So in decimal, we're going to add the exponents. So here 10 plus -5 becomes 5. Okay, that's our new exponent. We're going to multiply the significance. So 4.23 times 9.2, that's going to be 38.916. So now our result is going to be 38.916 times 10 to the 5. And then what do we do when we have this result? Right, we're going to normalize. So once we normalize, then what do we do? We round, exactly. So it's very similar. It's very similar to the addition in this part here, normalize and round. The difference is rather than aligning the values and adding them, we're going to add the exponents and multiply the significance. Okay, and then same thing. And of course, we need to determine if the sign. So if the sign of the final result is going to be based on the sign of the two inputs. So if two of them are positive, the result will be positive. Two are negative, the result is positive. And if one is positive, one is negative, the result is negative. Okay, so in this case, the sign is positive. Same thing for binary. If I'm multiplying two binary numbers, I'm going to follow the same steps. I'm going to add the exponents. Okay, so here my exponent is going to be -5. I'm going to multiply the significance. So here the final result will be this value over here. Then I'm going to normalize. So if I normalize, I get this value over here. And then I obviously have many additional bits over here. I can't have all these bits. So I'm going to round. So when I round, I get this value over here. Okay. And then finally, I'm going to need to determine the sign. So in this case, one input is positive, the other is negative. So my final sign is going to be negative. Okay. Okay, so to build hardware for this, you can imagine that it's going to be very similar to my addition hardware. The normalizing part, the rounding part, that's all going to be the same. The difference is rather than before I compared the exponents and I added the significance. Now I'm going to add the exponents and multiply the significance. Okay, so the floating point multiplier is has similar complexity to the floating point adder, but it's going to use a multiplier for the significance instead of the adder. Okay, and we can use just like we have for the exponents, it's the same thing. Rather than subtracting them to compare them, we're just going to add the exponents. And the floating point arithmetic in general that we do in floating point hardware includes addition, subtraction, multiplication, division, and then we also have an important part which is floating point to integer conversion. Again, just like with addition, multiplication, and all these other operations, they usually take several cycles, and they can be pipelined to optimize them, and we'll talk about pipelining later. Okay. All right, a final point regarding accuracy of the arithmetic. So someone asked me about rounding, and we'll talk about rounding now very briefly. So the IEEE standard specifies different ways of doing rounding. Okay, there's different ways. One of them is called having a guard bit. Another one, there's the round bit, a sticky bit, right? So basically, what they do is they tell you to intermediately have these additional bits in your hardware. So basically, if you're doing 4-bit addition, for example, you'll keep 5 or 6 bits around intermediately, and then at the very end convert back to 4. And whether you keep 5 bits or 6 bits and how you round these 5 bits or 6 bits, basically depends on, there's different modes for doing that, which involve these additional bits that the IEEE standard specifies. Okay, and the programmer can sometimes choose which one of these they want, or the hardware might implement one of them. So not all the floating point units in hardware implement all the options that IEEE specifies for rounding. Okay, and in most programming languages and floating point libraries, they just use whatever default option is available on the hardware. Okay, but if you're kind of a programmer that really cares about rounding and what gets rounded to what, then you have some floating point units don't give you the option, others might give you the option, and you have to kind of go into the lower level internals of the hardware to specify how you want rounding to behave. Okay, and the reason that not all floating point units support all options is because there's a trade-off between hardware complexity and market requirements. Okay, if you want to support all the options, it means you need to invest more hardware, and some people may not want to do that. They may not want to incur the additional expense of supporting all these rounding options. Okay, we're not going to go into the details of these rounding options too much. This is a very specific topic that is not very interesting for this course. But if you are interested in the specifics of rounding, feel free to kind of look at the textbook and see how these different rounding modes work. Okay. And with that, that is all for today. You can read more about what we covered today in section 3.5. Does anybody have any final questions? Okay, well, if there are no questions, then that is all for today, and I will see you next time. Bye, everyone.